This is the presentation video of the paper Behavior Tree-Based Task Planning for Multiple Mobile Robots Using a Data Distribution Service. The research is performed by Sungwoo Jung, Taekwon Ka, Jongyun Choi with Machine Learning and Control Systems Laboratory at the School of Mechanical Engineering, Yonsei University, and Inwon Jung with Hyundai Robotics. Our contributions of the research are as follows. We show how to use multiple behavior trees to operate multiple tasks of multiple robots in a separate task planning unit. The separate planning unit is regarded as supervisory task planning unit. Additionally, the supervisory task planning via a DDS domain are experimentally validated with 3 mobile robots. The supervisory task planning unit communicates multiple robots via DDS rather than the individual behavior tree to control a single robot communicates each other. The task planning and fault-tolerant function were completely separated. Each function is implemented with the behavior tree. Compared to previous studies, the task assignment can be done in the task planning unit. Typically, different network addresses for multiple robots are assigned to identify individual robots, which are managed using TCP/IP or a sensor network. However, such a control unit must know the network address of each robot. In this case, if a robot is powered down or if another robot enters a multi-robot cluster for replacement, the control unit must respond to new robots individually. Therefore, in this paper, we propose the DDS connection method for multiple robots to replace peer-to-peer connection, which has been studied extensively in the past. In distributed system environments, a DDS is data-centric and all participating robots in the DDS domain are allowed to be both data publishers and data subscribers. By writing data to the same DDS domain from any robot, additional participating robots can read the data. In a DDS, the standard data type is described by a topic name and value pair. This research is started from the concept of the behavior tree. To understand behavior tree, we briefly introduce the behavior tree nodes. First, a sequence node has one or more child nodes. If a child node returns a success, a sequence node ticks to the remaining child nodes. In contrast to a sequence node, a fallback node sends a tick to the next child node when a child node returns a failure. Unlike sequence or fallback nodes, which only execute one child node sequentially, a parallel node executes multiple child nodes simultaneously. The decorator node is used to assist with the configuration settings of child nodes. The action node receives a tick from a parent node, such as a control flow node, and completes an action. The condition node expresses if-then statements. For task planning for multiple mobile robots, we newly proposed the action client and server, and the asynchronous parallel node. If the subtree of a behavior tree includes action client or server, the subtree is indicated to the subtree client or server. The actions in a behavior tree can be executed by a single robot. To apply an action to multiple robots, the action is split into a set of action client and server. The action client sends a command to the DDS domain and the action server receives and executes the command on a real robot. The DDS action consists of 3 parts: a command that specifies the target task, a state that indicates the current state of the robot, and a return status that indicates whether the action has been completed, where the result returns success, failure and running, similar to the traditional behavior tree action. A behavior tree topology suitable for a single robot is presented in the left figure. When a robot is working with a given task behavior tree, it typically enters the recovery mode when it encounters an undesirable and undetermined scenario. Therefore, the recovery behavior tree for the fault-tolerant function of task is tied to the fallback node. However, if the task is not known to the robot in advance, it is necessary to learn the task to execute the task behavior tree. Let the unknown task node take charge of the task server behavior subtree and build up the known task behavior tree as a task client behavior tree before sending the task. In other words, the task behavior tree is split into task client and server behavior trees. By assigning task client behavior subtree to a task planner on separated hardware, task server behavior subtree is capable of sending the state and results in task client behavior tree using the following formula. The DDS topic between task client and server behavior subtree is shared by individual robots and the task planner in the DDS domain. The task planning behavior tree is presented. It was assumed that the robot task is the simple movement to the designated goal point. Therefore, the specific command to be sent to the action server is the goal point coordinate in the form of a topic. All goal coordinates are stored in the task planning BT with the set Blackboard action in advance. The task planning BT has 4 goal positions and the robot infinitely rotates on each of these goal position, as described by the repeat decorator node. Whenever ticks appear in navigation behavior subtree, the goal point is read from the action server in navigation behavior subtree as a topic and the robot performs global planning. If there are obstacles at the goal position or path planning fails as a result of obstacles in all directions, the recovery behavior subtree under the fallback node should be executed. Once global path planning is performed, the robots follow the planned paths. However, if planning fails, the global cost map is cleared. Similarly, if the robot cannot follow the path, the local cost map is cleared under the assumption of local planning failure. Before the global and local cost maps are cleared, we check whether the goal has been updated. If the navigation behavior subtree returns a failure, then the recovery behavior subtree is finally executed. In the first stage, a battery check is performed. If the battery charge is low, then the robot returns to the backup position. If the battery condition is fair, then the robot finally clears the entire cost map. It then spins, waits for seconds. To control multiple robots, the robots and task planning unit must be clearly distinguished. The task planning unit delivers tasks to multiple robots and receives real-time feedback regarding whether the tasks are being performed through the communication network. To implement one task planning unit for multiple robots effectively, the task planning unit should be capable of dealing with multiple task behavior trees for individual robots at once. To execute task behavior trees in the task planning unit for multiple robots, processes or threads for each task should be created. Each task in a process or thread has a single root node and different ticks are naturally generated. Rather than utilizing many ticks for independent behavior trees, one identical tick is more desirable for synchronizing multiple robots with one-rooted behavior trees. The test robots used in this research were developed by Hyundai Robotics. The robots have a differential drive, Wi-Fi for the DDS, sensors for tracking equipment, and a peripheral input-output module for delivery. This robot is mainly aimed at transportation in factories or providing simple delivery services to customers in hotels. The goal of the behavior tree for the robots is to transmit information through a DDS over Wi-Fi. The robot performs global and local path planning on an occupancy grid map. Once the global path planning for a given goal is completed, the robot performs path tracking. The goal of the behavior tree for the robots is to transmit the mission, for example, goal through a DDS over Wi-Fi. The DDS library was taken from FastDDS and the behavior tree library was taken from behaviortree.cpp. The action client and server library is the action in robot operating system Eloquent. To test whether the proposed behavior tree framework works properly, we attempted to control 3 robots to move to 4 designated goal positions, as shown in figure. The 4 positions marked by green circles are the vertices of a virtual rectangle. When one robot attempts to go to an adjacent vertex, the remaining robots also go to the designated vertex, as indicated by the red arrows. All robots repeat this process infinitely according to the actions and conditions set in the behavior tree. Thank you for watching our presentation.